Welcome back. At the end of part 2, here's where we ended up. We got this Iron Man fully surfaced in Moai 3D, and here is where we are heading by the end of this tutorial. A pitch perfect 3D model where all the surfaces are finely tuned to be one of the best 3D models of Iron Man outside of the original asset. Let's turn on the wireframe, take a closer look at these polygons. All right, so what we're going to do is import from Moai 3D into Modo. I'm using Modo. You can use Blender, Maya, 3ds Max. All the principles I'm going to show you for sub-D modeling will be the same. But we're going to take and stitch this up, clean it up, make some adjustments. And the result is this. You know, we've got this very accurate, clean 3D model of the Iron Man helmet. Of course, this is just a viewport image of it. We're not rendering or texturing, which might be something we could do in the future. It would be fun. As we move to the back side, if you look at the reference, I haven't done anything with these back areas here, but all the techniques that I've shown you and will show you apply. So if you wanted to, you can continue to finish out the back. I'm also going to show you how you can make these little details, the little bolted inserts that are on the mask and in the jaw on top of the head. Before we jump into the sub-D modeling, let's talk a little bit about where we're at right now and the two options you have going forward. One, I'm going to show you, and another, I'm going to point you in a direction of if you want to go that way. Okay, so right now, we are inside Moai 3D, and we have two options. We can either stay in Moai, or we can export into a poly modeling software. This is the route that I take. It's what I'm familiar with, so that's why it's what I'm going to show you. However, it is possible to stay inside of Moai 3D, and I am going to link you in the description to a YouTube channel that I found. I don't know how to say their first name properly, so I'm not even going to try and mess that up. I'm just going to call them Swagger. But the 3D modeling from Swagger is like top notch. And on that YouTube page, you're going to find this 5-part series that is showing a lot of advanced techniques for modeling a hypercar. I've watched all these. They're fantastic. And this shows the process actually very similar to the way we worked in the beginning. But Swagger stays inside of Moai and has a process for creating kind of like a pseudo sub-D model, and then uses the tools inside of Moai to refine it that way. And there's actually two techniques that Swagger goes over that would allow you to achieve comparable results all inside of Moai 3D. The reason why we can't just take this model and start to fillet the edges and soften things up is because we used the network surfaces. Actually, let me open up Moai and I'll show you. Check out this surface. If I turn on show points, see how it's mapping the entire back of the head, even though we've trimmed it out and we don't see that there. The way Moai interprets the networked surfaces is different than like a lofted surface. And so it's not as easy to just come in here and select these and fillet the edges. And I'll show you an example of that too, because if I zoom really close, look at these inaccuracies. And I think we modeled fairly accurate and we were using the same splines to work with. But you're going to have some of these inconsistencies because the nature of a networked surface, as I understand it, it's creating an average. And so you'll lose some consistency depending on how you network that surface. It's not going to be exactly perfect everywhere. And so you have to rebuild that surface. So I don't have the patience for this next step of the process. I think there's faster ways to do it utilizing other software. That's only my opinion though, because when I saw these videos from Swagger, I mean, they're excellent. And Swagger will show you two different techniques you can use to take it to that next step. So if you want to stay inside of Moai 3D, as much as I hate to kick you off my channel, that's where you need to go. Watch that car tutorial series and you'll see how you can apply that. And actually, it fits pretty well because the complexity of doing an Iron Man helmet and the complexity of doing a car are very similar. Few things are more challenging to 3D model than a car. And all the challenges that you have inside an Iron Man helmet directly relate. So, all right, so if you want to stay inside of Moai 3D, head over there. What we are going to do is export out of Moai 3D using settings similar to what we learned in this tutorial that I put out, and head on over to Modo. From there, we can use all of our poly tools to create a subdivision surface that will average and smooth everything out and create the result that I showed you in the intro. So here we go. Select the entire model, open up that export setting, and start messing around with stuff. I'm going to do divide larger than and divide smaller than. I'm going to adjust if you were in higher polygon count, and I'm going to turn the model around. And again, like in the other tutorial, which you can go check out if you want a more in-depth discussion, I'm trying to get something that maintains the shape, but has a relatively few amount of polys so that I can control the subdivision surfaces, which will make sense as we proceed. Here we are imported inside of Modo. It's looking good. And at this point, what I'm going to do is I'm going to start moving around the model, deleting edges, and trying to create a continuous flow of edges across these various surfaces that were created separately. So I delete some, and then I'm going to grab the verts, and you're going to see me stitching verts together, copying and pasting these separate items and pasting them onto their own. Inside of Modo, each surface gets its own group, its own container, and that's similar in Blender and other softwares. I need to combine them, put them on their own group so that I can stitch them together. So I'm going to add some edge loops where I don't have them. I'm going to be merging vertices together and creating one continuous surface. Our goal with creating one continuous surface is so that we can use something called a subdivision surface, a sub-D. A sub-D surface is a string of code inside of 3D software of your choice that translates the flat polygons, these 4-sided, 5-sided, 3-sided surfaces, and creates an average and smooths them all out. In order for that to work properly, all your vertices have to be welded together. All the edges need to be continuous so that you get this smooth result. You're also seeing me grabbing vertices and then sliding them along the surface. And the reason for that is to keep a good edge flow. Now inside of Modo, I can press tab to alternate between the polygon surface and a sub-D surface. So as I'm working, I'm clicking that and checking to see how it's looking, how the smoothing is working out. Let's break down the basics of a subdivision surface and what impacts the look of it. Direct your attention to the top left corner of your screen.
It's a box.
As I toggle between a subdivision surface and back to polys, you can see that it turns into a sphere. The sub-D is averaging the polys that are connected to create a rounded surface. So when the vertices are detached, it changes the way the sub-D surface works, right? It can't average these sides because the vertices are not connected. And if I join those together, so now they're attaching, but they're only attaching on that corner. If I do two sides, you see what I'm saying? You see what's happening? You see what's happening there? So that's the first part. You want all of your vertices to be joined. Okay, so now the next thing that a subdivision surface takes into account are edges. If we insert an edge loop and I run the subdivision surface again, now we start to get this little lumpy marshmallow. But here's what's cool. As I slide that edge, you know what? Hold on a second. Stand by. Okay, now we can see the edges a little bit better. All right. So as I slide an edge closer, watch what happens. Our marshmallow is a little bit more of like a dewdrop. All right, so as that edge slides closer to the corner, we get a more defined boundary. And if you do that on multiple sides, like these, so by using additional edge loops, you can control how rounded or how smooth of a transition you have as the surfaces change angles. So let's add a couple more edge loops all around everywhere. So a challenge that arises when you're doing a real complex 3D surface like the Iron Man mask is if you have a vertice that's not occupying the same planar space. Because we made a box, every one of these surfaces are all planar with each other. So we get this really nice, smooth result. But in like the Iron Man mask where we have more complex curves, if any of your verts get out of plane, then the sub-D is going to do its job and it's going to create a smooth transition. But that's when you get these, you can end up with these weird creases and inconsistencies. And if you're going for a really solid, clean result, you have to manage your edge flow and your vert placement. So as you're refining a model, this is an option that you can pull, say, a vert out of space a little bit to soften and kind of pillow out that corner. But as a best modeling practice, you want to avoid that condition whenever possible. A better way to control the softening of like a filleted corner, because that's essentially what we have, right? It's rounding off, is to control your edge loop. So if I space it out here, we get a more aggressive fillet, a softer corner. And as those edges move in tighter to this corner, we get a tighter fillet. So that's one way we control the quality of a surface. Back to the Iron Man mask, I've got reference up and I'm working on this nose area. Now, when you have, I'm looking at removing edges whenever possible, and I'm thinking about the flow of the polygons. When you have an n-gon like I do at this corner of the nose eye area, you see when I test the sub-D, it's awful. We can't do that. We need 4-sided faces. You can get away with 5-sided, but when you get more than that, you're going to end up with errors. And I'll speak a little bit more about 5-sided polys in a little bit, where you can get away with them and where they're bad. They're definitely bad around edges. You want to avoid that. So I'm stitching together on this corner of the eye area and just building out the poly surface so that I can smooth it. One challenge you're going to run into, so the tricky thing with sub-Ds is you can't just add more edges. If you just add more edge loops everywhere, you're going to remove your ability to control the surface well. There's an art to building out a subdivision surface and minimizing the amount of edges that you use. You can see as I move back into this nose area, I'm going to insert edge loops just to show you this is kind of where you might think to go. Well, I'll just add edge loops because I want to control, the rounding at the corner of the nose. I want it to be nice and sharp. So let's add edges in, and I need to connect to get rid of my n-gons. But once you do that, you can see that those additional edge loops, because they're not following the same spacing and curvature of the rest of that front part of the mask, you get creasing down the face of the mask, which doesn't work. So you have to get more creative, and it can be challenging in areas like this because you have a more intense area of detail, but you don't want to carry those edge loops across the entire mask. So what I'm doing here is you can see that I'm making adjustments. I'm thinking about creating quads, and I'm trying to split those. So I create like a chamfer at the bottom corner of the eye where I have one thin strip of polys that will help control that corner and give me a tight radius. And then up at the top, I'm trying to redirect my edge flow to go across the mask instead of vertical. If I go vertical, I have to add more edge loops. If I can try and, readjust that across the mask, then I can minimize the amount of edges that are required. And here we found the pretty decent solution. I'll touch on this again because this issue you'll see repeats over and over and over again in sub-D modeling, but you'll notice that I've created an edge loop, like a boundary condition that wraps around the top portion of the mask. So you give yourself a row of edges that's like a buffer to pull away from any other polys that are on the front side of the mask. and then I'm looking to experiment to look for a cleaner way to find the solution here. With a sub-D surface, you want to create polys where when you get that vertice, it's shared by 4 edges. So there's 4 polys beating to that point. If you have a condition where you have more surfaces meeting to that point, so it's, instead of 4, it's like 5 or maybe even 6, that star that's created can become a deforming issue. Now, the way I was trained to sub-D model was to stay away from n-gons like at all costs. But what I found, at least in my own work, and feel free to argue this with me if you see this differently, but I use n-gons if it helps with the result. So on the corner of an eyepiece, or where I'm trying to manage a more complex curvature, if adding an n-gon means that I don't have to add superfluous edge loops for the sake of having edge loops, then I'll do it. And I've got no qualms doing that. You know, if add the n-gon, add that 5-sided poly, do a sub-D, test it and see if it's actually working. And if you can get away with it, in my opinion, go for it. You do want to make sure that any n-gon, any 5-sided or more poly surface is pulled away from the edge, meaning that you at least have a boundary of edges splitting away from that corner that allows for clean quads that kind of march along that edge condition to give yourself a buffer from any n-sided polys. The way I'm showing you how to model some of this, like dealing with n-gons and how to manage them, my opinions on that in some 3D modeling circles is considered heresy. And I'm telling you that because I just want you to be as informed as possible. I'm showing you what works for me. It's worked on professional jobs. It gets the job done. It looks fantastic. I don't see a problem with it. But you have to have an eye to watch out for deformation, because when you add an n-gon into a sub-D surface, if you don't control the surrounding edges properly, or you get out of plane, you're going to create a deflection in the surface, which is going to lead to an imperfection. So it really depends on what you're doing this for. I do a lot of concepting work, which means speed is on my side if I just slam it in there and get going. What we're doing with this IRONMAN mask is a little more detail oriented than that. Regardless, the point is, take what I'm saying, add it to your educational bank of what you're studying and learning from. But keep in mind, as you continue learning, look for other resources. There are those out there who will contradict what I've just said about n-gons, and they will be damn near militant about it. And I'm not saying they're wrong. I'm just saying I'm right. No. Take that, you soup kitchen Nazis. Telling us what's right and what's wrong about our n-gons. All right, so they're a little right. Like, technically they're right, okay? And I'm probably teaching you a bad habit. So go learn from other smarter people. I'm just going to show you what works for me, all right? Gets the job done. It looks freaking amazing. I'm moving on. Another thing that I'll do while I'm modeling is switch to a matte cap. And a matte cap is like a different kind of shader, and it has like built-in reflections. So it's not accurate to anything texture or render based. It has its own like built-in lighting and like a reflective surface. It's going to allow you to really see how that surface is deforming, so you can fine tune it. So you can see in the front of this mask, I'm really trying to minimize the amount of edges that I have to control the surface with. The more edges you have, the more verts you have, and the more vertices you have, the more opportunities there are for something to get out of alignment and create little pockets of deflection, and you lose, reduces the quality of your model. So wherever possible, I'm trying to remove edges and reroute the edge flow in such a way that I get a good result. Okay, yada, 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 modeling. Scrubbing through. Let's just keep going. I'd like to make it just as long as possible and show you the whole thing, but I'm trying to keep it focused on new information for you. Okay, so yeah, let's slow back down around the top of the head, around this hood scoop area. And you can see, so I'm going to build in my own little padded row of quads. And you just slice those into place and march that all the way up to the edge of the top of the helmet. And this is going to give me, it does a couple things. If you have a continuous surface, that's how you're going to get that filleted type, tighter edge condition. But if you're but it also creates a buffer, a transitional bit of geometry into the rest of the smooth mesh. And once again, when we're dealing with this curved area that's cutting into the overall smooth part of the helmet, we're going to run into those deformation issues again. And I can try a couple different solutions. You're going to see that I test adding the edge loops, but once again, adding extra edge loops into the surface is going to cause like pinching, more deformation where we don't want it. We want a continuously smooth top of the head. Adding that buffer of polys along the edge helps us. I'm going to try and remove some edges off the corner, which I do. And then you're going to see I create this little 5-sided, you're going to see this is that condition I mentioned before. We have multiple quads, and the corners of those quads are all ending at like a star point where we have multiple edges, like 5 or 6, ending at one vertice. That's something else you have to watch out for in sub-D surface modeling, because you can create deformation issues there as well. When you do have them, you want to make sure you pull them far away from an edge condition and have a buffer of polys. So in the case of this little hood scoop at the top of the head, you'll notice that I have like 2 rings of polys that are conforming with the shape of that hood scoop. And they're tracking around and going up to the top of the helmet. And then I have that star condition towards the center of the helmet. And when that happens, you'll see it's also, if you go back and look at the model, or when I'm at the side of the helmet, you'll notice I have another one of those little star conditions as well. As long as I'm pulling that to the center of the surface and I'm handling the deflection of the vertices properly, it's not really an issue. Cruising along, we get to the side of the temple. Yep, there's another one of those little star conditions that I mentioned. And I'm going to kind of push and pull some of the verts around a little bit because I don't like the way it deflected inside near the eye. I want it to kind of bow out a little bit. All right, if you're a nerd like me, what's really fun is to study the way different materials are manufactured. And it's cool because if you look at the way that different manufacturing technologies, you're going to see that like a piece of metal that gets bent and formed is going to have a different kind of corner filleted edge. It's actually going to have a little bit of a bulge to it versus something that is like pressed into a mold versus something that's 3D printed. And that can kind of inform how much of a fillet you put in or what kind of a deflection. And so sometimes, and actually in the movie asset, you'll see some warping and some distortion a little bit at the corner points of the eye and around the eyebrow ridge and even around like the hood scoop area. And when light hits it from different conditions, even the nose area that we worked in, that's why I was okay with leaving some of that deformation there, because it can actually work to your benefit in a creative way if it matches the manufacturing model, the way the thing would have been made in real life. We know as 3D modelers that we're dealing with an issue there, but it can be a creative solution. It can actually add to the character of something that is not 100% perfect. So yes, we are getting into the weeds a little bit there. That's where the fun stuff comes in, especially if you're creating something that you want to have, some realism to it. I also love in the movie reference the eyebrow ridge as it moves into the center of the skull. There's an extra little bit of a bulge there, which gets captured in this 3D model thanks to the way we built this with NURBS and working off our reference. That carries its way all the way through the sub-D. And so as simple as it is, the top of the forehead, the subtleties of those curves, the subtlety of the way that surface rounds matches so closely to the film model. I like to see those kind of things, you know, when a plan comes together. You'll see me, this is kind of a Modo specific thing, I believe, but every software has its own version of this. When I mirror one side to the other, because we only really need to work on one side. That's the other great thing about sub-Ds. You know, you work on one side, mirror to the other, merge it together, and everything works. But sometimes my smoothing groups will get kind of hung up, or the way the normals are computed. And so what I have to do inside of Modo is clear all that out to reset it. And I haven't noticed that as much in Blender. But when you see those dialog boxes popping up, that's what I'm doing. It's nothing to do with the modeling process so much as managing what I'm seeing on the screen. Then we move down to the lower jaw area, and I'm going to skip through a lot of this because it's the same stuff. Now, here we go with, I've got a lot more edges. In this lower jaw area, I think it could be argued that I've got too many edges, and I think that could be fair. But in the reference, there was, for such a flat piece, it's not totally flat, and there was a lot of deflection, and the way like the corner of the jowl, like the jowl area down below the mouth, where there was like a pinching in the metal from the reference and from some other references that aren't even on the screen. It's just not straight. There was this like real subtle curvature that I think I nailed pretty well, but that's the reason for all these extra edges. If I spent more time, I could probably nail this with less, and that's always kind of the goal. But I just kept moving along. And here the process is the same. You get in here, you add edges where you need them, you stitch it up, you merge your vertices, cleaning up the surface, working on edge flow, keep on trucking. Okay, and I'm skipping ahead to the side of the jaw as it moves up toward the earpiece. And so that box example where I moved some of the edges away from the corner to soften the fillet in one side, but then the edges move tighter to the other corner and the corner becomes a much tighter chamfer. That idea is what I'm going to do in this jaw area, because studying the reference, that jaw piece, as it moves toward the temple, the filleting is more pronounced, and there is a well-defined plane change, especially in different lighting conditions. But as it moves toward the bottom of the jaw, that fillet exists, but it softens and spreads out into the underlying curvature of the jaw piece. A very subtle, but actually very tricky thing to land. That's made a lot easier because of our process of working with NURBS and the framework that we built. So I simply can manage that blending the same way that I showed you on the cube. But I'm working on edge flow, merging verts, and then, looking at reference and controlling that flow. And I like sub-D modeling for this reason. I don't always have time to do it. I've done it a lot more in my personal work, but it's kind of like solving a puzzle. And it's the kind of thing where it's cool to put on some music, grab some coffee or some tea, or put on a show, and you just kind of vibe, you get in the zone, and you're problem solving. A weird kind of meditation almost. Once you get it down, you got it. And then after that, it's, dealing with specific challenges where you'll learn more about different ways of approaching the routing of your edge flow. All right, so I'm going to cruise along here. Now, at some point, I realized in the film reference, there was a big change from the clay model to the final product. And that was where the gold mask tucked into, like where it met with the jaw. And there was a continuous line instead of like an offset. So I have to go back in the polys and I restitch and realign and move that around to fix it. Once we move into the top portion of the head, the cowl induction area, the hood vent, same process, stitch it all together, clean it up. Now for the earpieces, so I won't sub-D them. I'll just export a high density polygon model from Moai, and I'll leave it there. I don't have to touch it, no problem. I'll build out some eyes. If I were to spend some more time on this, I think I would have done the eyes a little bit different than I did, but the effect is still there. I think I would have done like a glass encasement on the front that gets backfilled, like the lights behind it, the glasses in front, and there's more of like a thickness to it versus it just being a single surface that lights up. And then I throw it in and do a little bit of a render. Lighting makes all the difference in the world, especially if you're comparing something. And the other thing is your camera too. If you're using a 35mm versus a 50mm, you're going to get a totally different look. But we're pretty damn close. On the top of the helmet, I use all the techniques that we've talked about. You can also extrude surfaces. So I just build in a channel of edges that I can then recess, and that becomes these inset slides in the top of the helmet just past the gold portion. And now we can look at how I created the indents, the little metal indents, the caps that are in the top of the skull and on the chin. So to do that, the process is to select a vertice, the single vert, and have that vert placed where you're going to put those little indents. Select the vert and then run a bevel. And when I run the bevel, it's going to bevel from the center of the vert and create new polygons, kind of like a star formation. Then I can select those edges and I run a script inside of Modo that does a perfect circle. So it changes the shape of the edges into a circle and keeps it on the face of the polys so it doesn't deform. There's the same way you can do that same thing in every other software out there. And then once I have that, I'll offset my edges and then extrude downward and build out the indent for the bolt. And then I will create a separate, I'll copy those faces, and on a separate group, I'll extrude those out and create the little screw head that sits down in there. All right, what do you say we wrap up this tutorial series, call it here? So we've gone through the whole process and hit enough of the major high points and challenges along the way that the process should be pretty clear. The roadmap is there. I encourage you to do studies like this that you can compare your own modeling to. That way you have a benchmark to hold you accountable. And through that frustration and that challenge, if you take it on, you will see marked improvement in your modeling ability. And then you can take that into your own personal work, your own creative work. And as we move forward, we're going to talk about design. We're going to talk about a whole lot of other really great stuff. But this tutorial series is good because it's one of the kind of cornerstones of building up your chops working with the software so that you're not limited. All right, I'm going to get out of here. All right, let's wrap it up. All right, on to the next one, on to the next adventure. Rabble, 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 rabble. All right, I'm out of here. Bye-bye. Bye-bye. Bye-bye.